And we're going to also be taking notes today to start our new unit on Newton's second law. We're going to be taking notes on forces and just some definitions and an introduction. So you are going to want some paper out for that. But before we get into the notes and going over what a force is and having me tell you, I'm just curious what you guys were able to come up with in your warm-up. The warm-up question says to type or write any 3 words that you remember about forces. Maybe try to come up with your own description or definition. Does anybody have any words they would like to share that you think of when you hear forces? You have anything, Emily?
Newton's law.
Newton's law, okay. Any other, what do you guys think a force is, if you try to define it? What do you think, Andrew? Any word that you think of?
Yeah, I guess like pushing.
Pushing. Pulling. Awesome. Those are the words I'm looking for. Okay, push, pull. We have Newton's laws. Any other words you guys came up with? Okay, now your warm-up question is going to be your words that you think of, so you can type whatever you want in there, and it should give you credit for it because we haven't talked about it yet. But hopefully you come up with words like pushing and pulling because you're going to see that that's also in the definition I'm going to give you. Okay, we're going to go through the notes. You do have an assignment today in My Open Math 301.1 Force Concepts Problem Set. But the definition of a force that I'm giving you has those same words that you came up with, Andrew. It says a push or a pull on an object resulting from an interaction with another object. Okay, so when we talk about forces, we are talking about things that are pushing or pulling on other things. And it is always an interaction between 2 different objects. Forces are also vector quantities. We've talked about vectors and scalars already quite a bit. But if you don't recall, a vector is going to be a value with both a magnitude and a direction. So when we talk about forces, it's not just you're pushing with this amount of force, you're pushing with this amount of force to the right or to the left. And we'll be diagramming those as well. But they have direction to them. Okay, so they are vector quantities and they are measured in newtons. Okay, so the unit that we use to measure force is called the Newton, and it is abbreviated with a capital N, like what you see on my screen. Okay, so again, it could be a force that is applied from a bat to a ball, like in the image right there. I think that's an older image. I think that might actually be George Springer. But you have that force, that push that occurs when the bat and the ball make contact. And there's a direction to it. And we could even give a number value, a number of newtons for that, which you'll be calculating later on whenever we put some numbers to it. Okay, so again, you are going to want a definition. So you could say the bat pushes the baseball forward, and that would be the force, or one of the forces actually, in that scenario. Okay, forces can be classified into 2 main groups. We have contact forces and we have field forces. Again, some more definitions you might want to write down in your notes. A contact force, as the name suggests, involves contact or touching between 2 objects. So these forces exist when an object is in contact with another object, when they touch each other, like the baseball and the bat. Okay, that would be a contact force. Or if you were to push against a door or push your neighbor, don't push them too hard. Okay, but that would be a contact force because you are touching. Okay, a field force, on the other hand, is a non-contact force, and that means that it's a type of force that exists between objects that are not touching each other. They are also called non-contact forces, or you will hear them called at-a-distance forces because they are forces that act at a distance. They act some distance away from the other object. It's still an interaction between 2 objects, but you have a force that doesn't require the 2 objects to touch, and yet you can still get a push or a pull between those 2 objects. Okay, so those are our 2 main groups. Can anybody think of any examples of a field force, a type of force that would act at a distance? What you got, Trey? Magnets. Cool. Yes.
A bomb.
I guess technically. But magnets is one of the ones I was looking for. That's kind of like a chain reaction if you had like an explosion of some kind, and it actually, you have air molecules involved. But they're not visible, but you're not. It's not really a true example of a field force. It's not a bad guess though. Yes.
Would gravity be a field force?
Gravity would be a field force, and those are the two that I would expect you to know: is force of gravity and then magnetism, which are examples of forces that can act at a distance. Okay, here are some examples of contact forces or forces between objects that are touching, and we could list more than what's up here, but if you want to jot down a handful of them, we have friction. Okay, you can have a frictional force that exists when one object is rolling, sliding, rubbing, or moving over another object. You can have tension, which we're typically going to associate with ropes or strings or cables where you have something pulling in there, although you could also talk about tension in like muscles. Normal force, I put up here, aka support force. This one you don't think about, but it's always there. That normal force right now, as you are sitting in your chair, the normal force is the force the chair is supporting you with. It's also the force that the table is supporting your computer with. So it's the force that a surface pushes back with. Air resistance, applied force, if you don't have it falling under one of these other categories, and usually we think of applied forces as people pushing against things. So if you were to push something, we would call that an applied force. And spring force, if you have a force from some kind of elastic object, which could be a spring, but it could be a rubber band or something like that. Okay, so those are just examples. And I already asked you that question. Could you think of any forces that don't require contact? And you guys came up with the two that I expected. I would not expect you to come up with the other ones, although it's possible, maybe, if some of you were, paying a lot of attention in your chemistry class, because the other forces that don't require these are the two that you came up with: magnets and gravity. That guy's falling out of a kayak. But you can have these forces without being in contact, the earth pulling down on a person, or magnets in this case pushing each other away, although they could also pull toward one another if you flipped that around. We'll talk more about magnetism next semester. Okay, but these are the forces between objects that are not touching, so these are your field forces, and there are only 4 of them. Gravitational force, which is actually what gives us our weight, and it's what we were talking about in the last unit when we said the only force acting on the object is gravity if it's in free fall. Okay, and that force is pulling objects down toward the earth. It's also pulling you down right now while you're in your chair, and it's what is giving you your weight. Okay, so your weight is a result of that force of gravity pulling on your mass. Electromagnetic forces, which we can talk about that together as electromagnetism, but you can also talk about magnetic force or electrical or electrostatic forces, which would all kind of be wrapped up in that electromagnetic forces. And then we have strong force and weak force, and we're really not going to get into those. I just want you to be aware that they exist, and they have to do with the makeup of the atom. Which is why I said you might know if you were, I don't know that you would be doing that in your first year chemistry class, but in AP chemistry, if any of you go in there, I believe they have a unit that involves strong and weak forces in chemistry. By the way, these 4 forces, gravitational, electromagnetic, strong, and weak, constitute the most fundamental forces in the universe. They're actually called the 4 fundamental forces. Okay, and so if you see any question about the 4 fundamental forces, it is referring to these 4 field forces. If you want to make a note, these are the 4 fundamental forces. You might see something that asks you a question about that. All right, so those are our field forces. So we have those 2 types. Today we're going to focus, at least for the first part of our notes, primarily on gravitational force because it ties into what we were just doing. Okay, any object with mass has a gravitational field. Okay, however, our masses are so small in comparison to the Earth that we can ignore our own gravitational field and only focus on field interactions between objects and the Earth. Technically, because you have mass, you have your own gravitational field, and that means that technically you and your neighbor have a gravitational attraction between you. It's just that compared to the Earth, you're very small. And so you don't find yourself being pulled toward the person next to you, rather you both find yourselves being pulled toward the Earth. Okay, that's basically what I'm saying up there. Okay, so we really only focus on those interactions between planets and people or objects on the planet, or later on we'll talk about interactions between like planets and moons or other planets, or the sun or whatever. You can talk about that whenever you have things with a lot of mass. Remember, gravitational force is a field force that results when an object interacts with a planet's gravitational field. The force of gravity is also called weight. Okay, so again, this is what we were talking about in the last unit when we were talking about those things in free fall. We said the only force acting on them was this one. Okay, and that's what was causing those objects to fall in that way toward the Earth's surface with that constant acceleration on Earth of negative 9.8 meters per second every second, all due to that force. So that's why I figured we would start here. Okay, but I told you it's also responsible for your weight, and so we're going to talk about calculating that today. We can calculate the force of gravity or weight of an object on Earth based on the gravitational field strength, little g. Remember, on Earth, that little g is negative 9.8 meters per second every second, or meters per second squared. So that's the same value that we saw last unit. Okay, so that little g, that's really acceleration due to gravity. That's what that means. And so this is the amount of pull on our mass. And the equation that we use to determine our weight or our force of gravity, again, it said in the last slide, this is weight, Fg. All we do is we multiply our mass in kilograms times negative 9.8, okay, times little g. Okay, and so this is the equation for weight or gravitational force. Fg equals m times g. And again, that little g is negative 9.8 meters per second squared if you're on Earth. If you're on a different planet, you'd have to use a different gravitational field strength for that mass of that planet, whatever it may be. So again, have this equation in your notes. So mass, again, that equation involves mass and weight, so we need to make sure we know the difference between the two. They're not the same thing. Mass is the measure of the amount of matter in an object, which is a very vague sounding definition, but that's how it's defined. It is measured in grams or in kilograms. I'll tell you right now, our standard unit, and for all of our calculations, we have to be in kilograms. So if you read a word problem and that word problem gives you a mass in grams, you will have to convert it. You might want to write down the conversion factor to help you remember how to do that conversion. There are 1,000 grams in a kilogram. So if I tell you that I have a 500 gram baseball and you're trying to do a calculation for it, you would have to do that 500 divided by 1,000 to convert it into kilograms. And of course, 500 grams is half a kilogram or 0.5 kilograms. But that's mass. Okay, weight, on the other hand, is the force of gravity acting on an object and may be defined as mass times the acceleration due to gravity. Again, in this equation, your masses must be in kilograms. I already gave you the formula for it. Fg equals mg, where that little g is your gravitational acceleration and where Fg is your weight measured in newtons. Okay, what that means is that your mass is just the amount of matter in you. Okay, whereas your weight has to do with how the planet that you're on, Earth, pulls on that mass. And so one of these will change based on your position, and the other one is constant, which we're going to get to and you're going to see questions about in your assignment today. All right, so weight versus mass. This bag of Cheetos will contain the same amount of matter. It's labeled on the package, 99.2 grams. It's mass. Whether it's on Earth or on the moon or on Mars or on Jupiter or floating in space, it will always have 99.2 grams of matter inside of it. Okay, that's what the mass tells us, is how much matter is in there. I'm sure you can imagine if you took a bag of Cheetos to the moon and you didn't open it on the way, you'd have the same number of Cheetos in there when you got there. Okay? So that is not going to change. Its mass will be constant. It will always have this much matter unless, of course, you start eating the Cheetos. Okay, so we're pretending we're not eating them, even though they're flaming hot, and I know you guys like those. Okay, so again, that's your mass. Okay, however, just like astronauts don't weigh the same on the moon, neither will that bag of Cheetos. Weight is the force of gravity acting on the mass, so it would appear weightless in space. It would appear lighter on the moon. When the gravitational field strength changes, so does the weight, but not the mass. The amount of matter in that bag will stay the same. yet it will not weigh the same. You can see the astronaut there, kind of bounding around trying to walk on the moon, and it's because of the difference in the gravitational field strength. You can see that it's takes probably a little bit of a learning curve to figure out how to walk with 1/6 the gravity. So anyway, but his weight is different, but his mass is the same, okay, whether he's on the moon or on Earth. All right, so let's do a calculation to practice using that formula. It says Jenny has a mass of 52 kilograms. How many newtons would she weigh on Earth? And then the second part says if 1 pound is 4.45 newtons, how many pounds does she weigh? Because obviously when we talk about weight, we don't normally talk about our weight in newtons. We talk about it in pounds. Pounds is also a unit of weight. It's just not our metric unit. Okay, but we'll do a conversion for it. Okay, so if I wanted to solve for how many newtons she would weigh on Earth, let's go ahead and write down the information I'm given. I know her mass is 52 kilograms. I know that gravitational acceleration on Earth is negative 9.8 meters per second squared, and I'm looking for my unknown Fg. I'm looking for her weight. Again, if it asks for weight, that's Fg. Okay, my equation, and I only have one, is this one. And so substituting in, this should be pretty straightforward. Mass 52 times g, negative 9.8, gives me her weight as negative 509.6 newtons. Follow-up question, why is her weight negative? When we talk about how much we weigh, we don't typically walk around and say, I weigh negative 130 pounds. We don't do that. But why is her weight negative up there? Weight's a force, right? I told you it's a vector. What direction is your force that's acting on you? If gravity's pulling on you, right, it pulls down. Okay, so that's why we get a negative number whenever we calculate our weight. You're going to get a negative number when you calculate your weight because the force of your weight is downward toward the Earth because that's the direction the gravitational field is pulling you. Okay, so this is also why we don't talk about our weight in newtons because everybody is going to look at that number and be like, oh my God, I weigh over 500 newtons. Okay, but we're going to convert it to pounds and you'll see that that's not actually that much. It just looks like a really big number. Okay, that conversion, if I want to figure out how many pounds it is, I divide by 4.45. That is 114.5 pounds. Okay, and again, if you were to say your weight to somebody, you probably wouldn't say negative 114.5. You would just say 114.5. You're giving the magnitude of your weight in that case. But it is a vector, so it does have direction. Questions about this calculation? Okay, again, to get from this to this unit, here was my conversion factor in the question. I just divided by 4.45 to cancel newtons, and that gave me pounds. All right, so again, pretty straightforward calculation. 3-variable equation. Shouldn't be too difficult. Just watch your units. If you don't have kilograms, get that first before you do that math. All right, let's try this one. Jenny's dog Jojo weighs 175 newtons on Earth. What is Jojo's mass? Okay, so again, we are given. Newtons tells me I've got weight, and it says weighs. So again, it's technically a negative 175 newtons. I know my gravitational acceleration is negative 9.8 meters per second squared, and so I can solve for Jojo's mass. Again, same equation I just used, Fg equals m times g. Plugging in, this time though, I am going to have to rearrange this to solve for m, but it's pretty straightforward. Negative 175 equals m times negative 9.8. I need to divide both sides by negative 9.8 so that I can get that variable by itself. So dividing both sides by negative 9.8, we'll cancel it over here. And then, of course, over here we have this, which equals 17.86 kilograms. Again, when you do this calculation, the mass that you get will be in kilograms. And if you use kilogram or use a mass for the calculation, it needs to be in kilograms. All right, so that would be Jojo's mass, 17.86 kilograms. All right, so again, I think the equation should be pretty straightforward. It's a fairly simple calculation. Okay, follow-up question. How would Jojo's mass compare on the moon? Would Jojo still have a mass of 17.86 kilograms on the moon? Mason and Andrew are both nodding yes, and that is correct. The mass will stay the same. That's the amount of matter in Jojo. That will be the same. but his weight would not. Again, weight will depend on your gravitational field strength. If you're on the moon, you have different gravity and therefore a different weight, but your mass will be the same. If Jenny and JoJo both jump off a high dive, who will experience the greater acceleration toward the water below? This is really more of a question that would have been on your test, and you should know the answer to it. Who's going to have more acceleration? One of them's heavier than the other. Does that matter? Doesn't matter. Okay, they're going to have the same acceleration. They both experience the same acceleration of negative 9.8 meters per second squared. Again, if you're in free fall, that's your acceleration regardless of your mass. Okay, so if they both jump off that high dive, they will both have the exact same acceleration. All right, how can you detect if a force is acting on you? We're going to talk more about this tomorrow, but you can determine if there's a force acting on you based on its influence on the object's motion. Sometimes those forces can cause a change in the motion. So sometimes you're going to see objects speed up, slow down, or turn because of forces. But right now, you're not speeding up, slowing down, or turning, and yet there are forces acting on you as well. There are always forces acting on objects, no matter their motion. Maybe it's gravity. Maybe it's the upward force from your chair. Maybe it's friction. And sometimes those forces can cause a change in your motion, and other times they're just doing nothing at all, like what's happening right now. Okay, and so when we start to put numbers to it, you'll see why sometimes you get a change in motion and sometimes you don't. All right, so these are the same list of forces we had earlier. It's just I didn't define them yet. So if you want to copy down some quick definitions of each of these, you can. But we have tension force. If you have tension force, you're going to represent it F sub T. Tension force, again, is the force within a rope, string, or even your arm when you're holding or pulling up an object. Gravitational force is F sub G. This is the force from an object's weight. It always points toward the center of a planet or straight downward, and we can calculate it. Fg equals m times g. Applied force, we're going to abbreviate F sub A, and it is the force from a person who is pushing or pulling on an object. Normal force, F sub N. Again, you'll notice all of these just have the first letter from the name. It's going to continue. Okay, F sub N is the force that a surface pushes back with. It's the support force, and it is always perpendicular to the surface. Your table right now is pushing perpendicular to the surface, straight upward on your computer. Your chair is pushing straight upward on you. Okay, the floor, if I stand on it, is pushing straight upward on my foot. Okay, that is the normal force from those objects supporting my weight. Okay, or the weight of your computer. Friction, F sub F, is a force that opposes motion. It is always parallel to the surface. You'll notice this one is always perpendicular. This one's always parallel. It is in the opposite direction of the object's motion, or the object's desired motion, if you will. Okay, but it is the result of two objects that are rubbing against each other. We can actually calculate this. This is the formula. We're going to talk more about it later. But F sub F, or force of friction, is equal to, this is a Greek letter called mu, mu, times Fn. Okay, and we're going to, again, talk about this later. If you want to copy it down now, you can, but you don't have to worry about what any of it means yet because we haven't talked about it yet. Spring force, the last one, F sub, where is it at? F sub S. Is the force that restores a spring back to its original shape when it is stretched or compressed. If you pull, and it doesn't have to be a spring, let's talk about a rubber band. If you pull a rubber band, you can feel it pulling back against you, and you know if you let go of one end, it is going to return to its normal shape. That's the spring force. Okay, it is what restores a spring or any elastic object back to its original shape when it has been stretched or compressed. We can also calculate it. Again, we're not going to use this equation yet. We'll talk about it later. But F sub S, or spring force, absolute value of it equals K times absolute value of X. And again, you don't have to know what those things mean yet because we haven't talked about them. Only one you should know right now is this one, Fg equals M times G. Okay, so again, these are different types of those forces that we talked about earlier. And those are the main ones that you're going to see and the main ones that you're going to have to label on diagrams. That's why I want you to know how to abbreviate them. Okay, but again, F sub whatever that first letter is typically the way you're going to want to do that. By the way, if I'm going too fast for you, this is on slide 17. I do need to make sure that I've posted this because I don't think you'll have it yet, but you can go back and look at it. It will be there later today if it's not there already. I don't think it is though. All right, so I said that we need to be able to identify and label them because you're going to be diagramming them. We're going to be drawing diagrams in this unit. You're going to be graded on your ability to draw these diagrams. They are called free body diagrams, and if I were you, I would write down the instructions for constructing a free body diagram, which I have abbreviated FBD. You will see that throughout the unit as well. FBD is free body diagram. First of all, a free body diagram is a diagram used to show the relative magnitude and direction of all forces acting on a system. So every force acting on whatever object you choose to be your system in that particular example. So the steps for constructing a free body diagram are to identify the system. What is the focus? What are you being asked to analyze? If I'm talking about, pushing a shopping cart, then your system would be the shopping cart. If I'm talking about, hey, let's talk about the weight of your computer, okay, or the normal force acting on it, then your computer would be the system. It'll probably be identified for you in the question. Okay, but that's your first step. Step 2, determine the types of forces present. What forces are acting on this object? We had a whole list on the previous screen, so think to yourself, do I have anything elastic here? No, not really, not with the computer on the desk. But I do have force of gravity, okay, and so you would start to identify the forces that are present and acting on the object, and then determine what direction those forces are acting. Okay, lastly, you'll actually draw the diagram, and you do that by drawing a box and adding arrows for each existing force in the appropriate direction, and then labeling each force arrow according to its type. We're going to do an example in a second. So for right now, you just need to write down the directions for doing this, and then once we do the example, it'll hopefully make more sense if this doesn't quite make sense yet. Okay, so we're going to identify the system, determine the types of forces, determine which way the forces are acting, and then draw it. Okay, so those are basically the steps abbreviated. But this is going to be a diagram that shows all of the forces with both their magnitude, so the length of the arrows will be relatively appropriate. Okay, so if you have two forces that are the same, then they need to have the same length. Okay, if one of them is a greater force than the other, it would need to be a longer arrow than the other. That's what it means by relative magnitude, okay, and direction of all forces acting on a system. Okay, so let's go ahead and take a look at an example, and we're going to go through these steps. Okay, we're going to do a book is at rest on a table. You can pretend this is your computer is at rest on a table because it is in front of you right now. Okay, draw a free body diagram showing all forces acting on the book. Okay, so my system is the book, but that's step 1, identify the system. Okay, so because I'm being asked to show the forces acting on the book is my system, not the table, the book. Okay, so step 1, system is the book. Step 2, what are the forces? I know that I have Fg because I know that there's gravity on Earth, and so I know that that book has weight. I also know that that book is not falling. Okay, if the only force acting on it was Fg, it would be in free fall. We know that from the last unit. So I know that the table is supporting it, and we talked about that support force is called the normal force. So I have Fg and Fn. Okay, and those are really the only forces acting on this. Okay, so that's step 2. We've identified the forces. Step 3, what direction are those forces acting? Okay, Fg is downward and it's always downward, and Fn is upward and it's always going to be perpendicular to the surface, and my table is level and so it'll be straight up. Okay, so I have Fg is down, Fn is up, and your last step is to draw it. That's step 4, draw the picture. So I have the box that represents my book. You can even write the word book inside the box if you want. And then I have Fg with a downward arrow. Again, forces are vectors. We can represent them with arrows. And I have an upward arrow for Fn. Okay.
Fn, it wouldn't be on every equation. What if it's like
unless you have something falling. Or if maybe it's hanging from a rope, then yes, you'll have Fn most. If you have something that is on the ground or on a table, on a surface, yes, you will have Fn every time. But if you have something falling where there is no surface underneath it, or like hanging from a rope, then no, you will not have Fn. But otherwise, yes. Questions about the free body diagram for this? That was a good question, Mason. All right, let's look at another one. A ball is dropped from the 4th floor atrium. Some of you guys did this 2 weeks ago. I can't remember. Was that last week? Draw a free body diagram showing all forces acting on the ball just after it's dropped. Okay, so my system is the ball because it says to draw the forces acting on the ball. Okay, what forces are acting on this ball? Gravity. Anything else?
Air.
Okay, there could be air. I'm going to assume there is no air, but that's not a bad answer. If I had air resistance, I would include that, but I'm going to assume that this isn't free fall. Okay, so I'm just going to have FG, just like last unit. If we have an object in free fall, the only force acting on it is gravity. So I'm just going to do that one. Now, if I had said there was air resistance, and I really should have said that there isn't here, to be fair, then I could have also included that arrow. Okay, but I'm going to just do FG, which is downward. That's the direction of it. So if you have an object in free fall, this is what the free body diagram looks like every single time, because every object in free fall, the only force acting on it is gravity. Okay, so that ball, or if you drop your pencil, or if it's an elephant, it doesn't matter. The only force acting on that object is the force of gravity, unless, of course, you're told to include air resistance, in which case you would have an upward arrow as well. Any questions about this? Yes?
So you can always draw just a square?
Yeah, we use a square to represent everything. Okay, so don't try to draw like an elephant. If I say an elephant is in free fall, don't try to draw an elephant and then an arrow. No, everything is a square. So that's an awesome elephant or an awesome ball or an awesome whatever. Just draw a square. Okay, so don't try to make your picture look pretty. If I ask for a free body diagram, I don't need an artistic. Okay, I just need the forces. All right, guys, so for the rest of the class period today, which you guys have about 15 minutes, so you have time to ask questions as you're working on this if you need to. You have an assignment in My Open Math 301.1 Force Concepts Problem Set. I think it only has 9 questions, so you should not have any homework. But if for some reason you don't finish it in class, it is due tonight by 11:59 p.m. Obviously, as you're working, if you have questions, you may ask me, you may ask your neighbor. But go ahead and get to work on this, and if you have any questions, please let me know.